So what I thought I would do today is switch back from the super basics of collider physics to talking about more theoretical questions about what we might actually be learning or seeing at the TeV scale. And at least for me personally, I've been thinking about physics at the TeV scale for exactly 20 years. So I entered graduate school, I started grad school exactly 20 years ago, almost exactly 20 years ago. And really for those 20 years, thinking about this set of questions has been the, at least for me, has been the sort of central, main, most important set of things to focus on. Like many people, you work on many things, but this is a thing which is, was, and continues to be nearest and dearest to my heart. So I've thought about it for 20 years, and it doesn't mean that I have anything particularly more valuable to say about it than anyone else. But I thought it would be fun, since I'm the one talking and you have to sit there and listen, to tell you what I think is going on. Okay? Now, of course, it's highly uncertain. All of these things we can, obviously it's highly uncertain for all of us because we don't actually know what's going on. This is my feeling for what's going on. It's at least a picture for what's going on that, in which all the various hints, qualitative and quantitative hints that we've gotten for what might be happening at the TeV scale, all of them have some purpose. Despite the fact they seem to be at cross purposes, they all actually all make sense simultaneously in the picture that I want to tell you about. But really, even that picture is a first order detailed elaboration on the zeroth order picture, which is that it seems to me very likely that, that nature is supersymmetric, if not at the TeV scale, not very far from the TeV scale. And anyway, supersymmetry is such a standard part of thinking about physics beyond the standard model that I will talk about the sort of a little bit of the basics of standard Suzie phenomenology early on in this talk, but we actually have dedicated talks next week about the status of natural Suzie, both theoretically and experimentally at the LHC. So I won't go so much into that in detail, but I'll talk about it. So really I want to talk about what the sort of supersymmetric picture of the world is, and looking a little more closely what at least my feeling is for the most reasonable way in which supersymmetry might be realized, which is the sort of minimal picture of split Suzie. And one reason for talking about it is, quite apart from my own feelings, which could be completely wrong, it's an example of a scenario which also forces you, if you care about particle physics and phenomenology, to think about all kinds of different possible experimental probes for going to higher energies, and not just collider physics. So that's something I'll come back to at the end. It's telling you about the various ways that things might evolve, and where we might be headed in 5, 10 years more, a little more concretely. But of course, high energy probes like the LHC will be extremely important if this picture is true. Much higher energy colliders could be absolutely crucial. Human beings know how to build 100 or 1,000 TeV colliders. This is not something that we have technological problems to do. We have no idea how to do it. In fact, people are starting to talk now about 100, 200 TeV colliders. You just need a 200-kilometer tunnel or a 100-kilometer tunnel somewhere. We can build 100-kilometer tunnels. You don't need magnets much more powerful than the magnets we have. So these are things that humanity can do. And so going to a factor of 10 to 100 times higher energies is definitely something that's possible, certainly in the time span of relevance to your career. And this is the sort of thing that more people are starting to talk about, thinking about what the 30, 40, 50-year future might look like. And anyway, this is one of the scenarios, not the only one, but one of the scenarios where first the LHC is very important, 100 TeV or 1,000 TeV collider is very important, and scores of other things, indirect probes of high energy physics and so on, are also important. So it's so minimally, apart from my feeling that about the plausibility of this picture, it's also an excuse to talk about the multi-pronged approach for thinking about experimental probes of fundamental physics. Okay, but, and that's really something I want to encourage all of you to think a lot about, to think as broadly as you can about different possible experiments, different signals, different probes that we can have for fundamental physics. That's going to be an explosive growth opportunity in the next, 5 to 10 years. So anyway, we'll talk about it a little more later. But first, before getting to Suzie, I want to just going back to naturalness, just in general, I want to summarize a little bit the pros and cons of taking naturalness seriously, and then we'll talk about it in the context of Suzie. So the pros we talked about already a couple of times. Naturalness is correct in condensed matter systems. This is really the Wilsonian viewpoint. Naturalness explains why it is when you walk around you don't see effective theories with light scalar fields willy-nilly all over the place, okay? We can get such effective theories in condensed matter, but only when there is some fine-tuning that's being done from the outside. So we can see that. Of course, we're all agreeing that there's some kind of interesting theoretical argument that it takes fine-tuning to make scalars light, and maybe there's something wrong with it. So I'm saying apart from that, do we have positive indications that this idea is on the right track, other than just that theoretical argument? Well, this is, I think, a very good one. It has worked, not in condensed matter system, but in the context of particle physics, it has worked before. And we mentioned the example of the classical self-energy of the electron, the mass splitting between the charged pion and neutral pion, and KK-bar mixing are 3 examples in the last 100 years of some UV power-sensitive quantity where new physics came in at exactly the scale it was supposed to come in order to address the problem. So it has worked before even in particle physics, 3 times in the past 100 years. There's now a somewhat more indirect argument, but if you believe that there should be new physics at the TeV scale, and can't be random new physics, so it's not just likely going to be just a single particle here or there. If you think there's some sector of new physics at the TeV scale, then there could be a plethora of new particles. And we also know that baryon and lepton number, for whatever reason, are very good symmetries. Okay, well, of course, we'll come back to put that on the con side in a second, that the beautiful standard model explanation of the accidental symmetries is lost if we have a lot of new physics at the TeV scale. But for one reason or another, baryon and lepton number are good symmetries. So let's just imagine that they're essentially good for all intents and purposes that we want to talk about. Then just that reason makes it very likely that many extensions of the standard model will contain a dark matter candidate. And I'm saying it in this way just to emphasize this has nothing to do with R parity or this or that accidental discrete symmetry. It's a slightly more general reason. If baryon and lepton number are good, and there's any new particle which is a fermion which does not carry baryon or lepton number, it has to be stable. Just it's a 2-line argument, but I want you to think about it yourself, because just think about what its possible final states could be, what particles it could contain in the final state. If it's a fermion, and you'll see that the only way it could possibly decay would involve baryon and lepton number violation. So if baryon and lepton number are good, then any new fermion, which is neutral under baryon and lepton number, will be stable. And then we have the usual qualitative WIMP miracle argument that tells us because it's also at the hundreds of GeV scale, it will have roughly the right relic abundance to be dark matter. In other words, naturalness is a reason to expect lots of new particles at the TeV scale, and it's very easy for them to be stable. So it would sort of predict that you should have lots of new particles, and the fact that they're near the weak scale is not accidental. So I'll put that as a pro. It's not as strong a pro, but it is a pro for this line of reasoning. Now, that's just on very general grounds. If we think in the context of supersymmetry, just jumping ahead for a second, There is another humongous pro, which is the supersymmetric picture of gauge coupling unification. Okay? So if you think there's Suzie, we look at this picture for the running of alpha 3 inverse, alpha 2 inverse, and alpha 1 inverse. Okay? That's a precision unification at the percent level near the gut scale. That absolutely didn't have to happen at all. The only motivation for putting all this supersymmetric particles at the TeV scale is naturalness. That's otherwise they could be anywhere naively. So the fact that that falls out seems to be another big, big pro to my thinking. That picture seems unlikely to be an accident, and I think should be taken extremely seriously. By the way, some people say, oh, if you're starting to tune and things like that anyway, why do you care if there seems to be a 1%, that the coupling's unified at 1%? You're going to tune a lot for electroweak symmetry breaking, for the hierarchy problem, whatever. But there's a difference, of course, that the tunings we're going to talk about, perhaps tolerating in a little bit, all involve things that have big dramatic impact on infrared physics, right? It's not that you say you tune and you allow yourself to tune anything willy-nilly, right? The things that are likely to appear tuned in the second picture we'll talk about are going to be things that have a big impact on low-energy physics. Whether the coupling constants do or don't unify at the gut scale has no impact on low-energy physics whatsoever, okay? So it's exactly the things that seem to be clues about parameters or phenomenon that could not possibly have, in any reasonable sense, an environmental or anthropic interpretation, seem to be clues that deserve to be taken seriously. Okay? So that's why it's going to make sense, at least for my thinking, to simultaneously talk about potential tuning for the cosmological constant or for the hierarchy problem while trying to maintain success like that. But anyway, jumping ahead a little bit. All right. So these are pros. Now, what were the cons? From day one, day one here is, 1978 or whenever, 77, whenever people started taking the hierarchy problem seriously, okay? The cons from day one were, big con, what about the cosmological constant, right? The elephant in the room, as not de-emphasized. Another con is, if there's all this stuff there, why didn't we see, why no large, why is the standard model explanation of approximate symmetries not violated? Okay, so this is what we talked about, that all the scales have got to be hundreds to thousands of TeV, or even much higher for baryon and lepton number violating operators. And these were not problems that had anything to do with experimentalists or probing anything. This is just theoretical things or things we knew about the world already, are something on the con side. Now, this one was so enormous that in 1978, people just ignored it, okay? And in 1978, it was okay to ignore it. Well, it wasn't okay to ignore it, but as Nazi also emphasized, many people thought some very deep mechanism, something we didn't know about quantum mechanics and gravity or something, might just make lambda 0, so we wouldn't have to worry about it. And anyway, so it does no good to stare at your navel and say the problems are hard and do nothing. So so also pragmatically, it makes sense. You ignore it, you move on. This one was more interesting, okay? Because this one, on the face of it, is a bigger, is much more concrete. There's scores of operators. It has nothing to do with these deep mysteries. And the attitude towards this one was interesting, because these were thought of as not problems, not cons, but as opportunities to learn more about what the picture at the TeV scale really was. Okay? And in a sense, this is why the field of physics beyond the standard model building, existed. Okay? That's the non-trivial part of this field, is solving the hierarchy problem, while maintaining an explanation of that. Okay? So it has some special structure. It's not garden variety. Flavor is protected for some reason. As Nati emphasized, that already was a big problem for the strong dynamics kinds of explanations. Raman will tell us more about the sort of modern ways of thinking about flavor and all the other issues associated with strong dynamics. At least in some part of his talks, he'll talk about that. But anyway, this is why the subject existed. It was a large part of the non-trivial part of the subject, was trying to keep things natural while avoiding these problems. Okay? And so that's the status for a long time. Now, of course, experimentally, what started happening is the limits on these things got better and better and better. We continued seeing nothing, right? We continued not seeing anything at accelerators. And finally, today at the LHC, when we're sort of deep in the heart, well, let's say we're in the middle of the heart of the territory, where new particles should be directly produced that are relevant to the hierarchy problem, we can add a new con to the list. Where is everybody? Okay? And that's the strange situation we're in. We have these we have these just facts that are just true. We have these gifts from above. This one even more than that, but these are like, how could you possibly see this picture of the couplings unifying to percent accuracy, and then you also get dark matter. You know, this is the night dreams of the model builder in 1990. It's sort of so obvious this is the right picture of the world. Big arrow pushing us this way, but now we have these things, especially those, but that, and of course a big way that is hard to quantify how big, pushing us the other way, and as I said already in the first lecture, this is why this is such an interesting time, right? So we don't have a clear hint one way or the other about how things are going to break. And that's what we hope to get some clue about from the LHC. Okay, so keeping this in mind, let's talk about the supersymmetric solution to the hierarchy problem. And some intermediate things. And I just want to quickly remind you again, the particles you really need, who is needed for Suzie? Who is really strictly needed, absolutely needed, for Suzie to solve hierarchy problem, at least near the TeV scale. All right? Well, we said it already. So the biggest quadratic divergence in the standard model comes from the top loop. Okay, so this is giving us a correction that goes roughly like 0.3 times the UV cutoff squared. In Suzie, that guy is canceled by a loop of the stop. And independent of any ultraviolet motivations, picture where it could come from and everything, just if the basic argument is correct, that there's just no tuning, so we can just put 0.3 lambda UV squared comparable to 125 squared, and that tells us that the stops should be lighter than, let's call it, about 400 GeV. Okay? And I want to emphasize this is not something that's going to change. It's not something that if 3 years from now we'll say, no, we didn't mean that. It was really 800 GeV. This is not a moving goalpost. Okay? There's nothing we can do about it. If the stops are heavier than 400 GeV, there's some degree of tuning. Is it too much and so on? That we can talk about later. But if there's going to be just no tuning, the stop should be lighter than 400. In fact, and this is why I went through the example, some of the previous historical examples, when naturalness has worked properly before, it was not the case that the corrections were comparable to the leading effect. The corrections were small compared to the leading effect because the theory had a weak coupling factor. Our theories have a weak coupling factor, and it would be surprising if the corrections were right comparable to the size of the leading effect. In analog of the classical self-energy of the electron, that would say that the new physics came in right at the classical radius of the electron, right? And it didn't. It came in 137 times earlier. We'll come back to this in a second as an aspect, I think, of the more refined and little hierarchy problem associated with the supersymmetry. But anyway, so this is generous already. Okay, this is generous already, but still, independent of any extra interpretation, the stops have got to be lighter than 400. Okay? Now, that's not the last particle we need. We can say, what about everyone else? Naively, let's talk about the muon in the loop, or an electron in the loop, or other guys. Well, those Yukawa couplings are so tiny, naively, those particles could be at thousands of TeV, and it wouldn't make hundreds of TeV, and the quadratic divergence would be just fine. So we'll come back to them in a second. Okay? I'm putting so the stop has got to be lighter than 400 or down. Okay, now, in turn, in order to keep the stop lighter than 400, the stop itself has these kinds of corrections from gluons, so strong corrections to the stop mass from gluons, to be lighter than about 1.2 TeV. Okay. All right. And once again, this is very generous. There's no logarithms. There's no enhancements whatsoever. You know, this is in almost every concrete ultraviolet theory we might imagine, the effects are bigger than this. The particles would have to be lighter than this, but this is totally unavoidable. Okay? If we don't see the spectrum, then we have unavoidable tunings. The unavoidable tunings are the product of two factors, 400 over m stop squared, everything in GeV units, and 1200 over m gluino yeah, let me say it like that. Okay, we have these unavoidable tunings, and so that's something that we're starting to learn about supersymmetry. Right now, the stop masses, I mean, it depends a little bit on the kinds of, well, we'll have talks about this next week, but we are definitely pushing this already, okay? So, and depending on how exactly you're thinking about it, we're into the 10% territory already, as of today, for what's going on with Suzie. The stops are probably heavier than 600 already. Anyway. Okay, but let me just complete the picture for who you absolutely need. What about the first two generations? What about the other? Well, so we need to have the Electroweak Inos have got to be around, but they could be in excess of a TeV or so, just because the weak couplings are smaller than the top Yukawa coupling. There isn't a color factor. So those quadratic divergences could be cut off at a TeV, no problem. So we could have Winos, all that stuff. The Wino at 2 TeV is fine as far as naturalness is concerned. 1 TeV is fine. And that's, and we're not going to directly probe Winos that heavy anyway. But can we just get rid of the first two generations totally? Can we hoof them all the way up to arbitrarily high scales? And we cannot. And the reason is that if you make the first two generations, I mean, again, you can't judge everything talks to everything else through the standard model interaction, so you can't super badly break supersymmetry in one part of the theory and not have it feed in everywhere else. And in particular, if we have large soft masses for the first two generations, let's say for the first two generation quarks, then there's a two-loop running of the soft masses of the third generation, or the light guys. That's the leading contribution to the running of one scalar mass off of other scalar masses through the gauge interactions. And it's two loops, but you know, there's an 8 from color, for 8 pi squared, it's proportional to the mass squared of these heavy guys. And, of course, it's logarithmically enhanced. So whatever high scale that you're starting to run from down to the mass of these heavy guys. So despite the fact that it's two loops, it's log enhanced, and of course it's proportional to the mass of the heavy guys. That means that if you're starting to run from any reasonable high energy scale, even a few hundred TeV, you can't make those first two generations much heavier than even 30 or 40 TeV. That's sort of pushing it. If you're starting to run at the gut scale, you can't make them heavier than 5 TeV, okay? Because you induce a mass squared for the other guys. And it's a log, so it's calculable, and the sign is negative. So it's particularly bad because there's a large negative contribution to the soft masses of the third generation. You don't want the stop to have a negative mass squared, break color. It's fairly disastrous, okay? So that tells us that we cannot, just purely from the bottom up, we can't split the spectrum arbitrarily. And if it's going to be natural, our friends have got to be very light, okay? And that's what we're going to probe directly, and we'll have talks about that next week. But even the rest of the superpartners cannot be very far away. And if we're starting to run from any high scale, they're definitely beneath 5 TeV. Even if you really push it, there may be 10, 15, something like that, okay? All right. There's one final important particle that we should talk about, just to make a, well, which is that here we're talking about the radiative corrections to the Higgs mass. But in supersymmetric theories, the Higgs comes partnered with the Higgsino, and there's a supersymmetric mass term we could write down for the Higgsino, the mu term. So we know we haven't seen the Higgsino, so naively the mu term has got to be there. And the mu term gives you just a tree-level contribution to the mass of the Higgs. So if mu was 1 TeV, that's already like almost a percent tuning, right? Because there's a 1 TeV squared contribution to the mass of the Higgs already. So at least naively, you need the Higgsino to also be light. And if it's really natural, it's got to be around lighter than 200 GeV, let's say. 125 would be best, okay? So right around where the Higgs is. Now, I'm just putting a tiny caveat on this, because this is not strictly needed from a bottom-up point of view. And that's because it's the only reason we infer the need for a mu is that we want to give the Higginos a mass. But the Higginos do not, the Higgsino mass does not have to be supersymmetric. It could be a genuinely Suzie breaking effect. And if it's a genuinely Suzie breaking effect, it's possible to give the fermions a mass while not giving a scalars a mass. For example, you could imagine a theory of the low scale of supersymmetry breaking, where the Higgsino mass comes from a higher dimension operator in the Kähler potential, like d alpha h up, d alpha h down, and there are some Suzie breaking spurions in front of it, okay? So that could be the origin of mu, in which case the correlation between where the Higginos are and the Higgs is lost, okay? So that is a caveat, so it's not, this is nothing you can do about this. That is a little small caveat there, but I don't think it's all that reasonable. It seems quite likely that the Higgsino would also have to be light if it's natural. Okay, so this is the bullseye. Okay, but this right here is the Suzie bullseye, and as I said, it's being pursued right now, and already it's in, I think, reasonable to say it's in 10% territory, and for the reasons we talked about last time, the factor of 2 going to higher energies at the LHC isn't a small deal because of this fact that Hadron colliders, that the rate for producing particles of a fixed mass scales like a high power of the center of mass energy of the machine, ECM to the 5th or 6th. So we're buying this factor of 100 in the rate for producing these particles when we go to 13 TeV, and that's why the kind of probes that we're going to have starting in 2015 are 100 to 1,000 times more powerful than anything we've done already. Okay? Eventually, we'll hit stops at 1.2, 1.3 TeV, just from direct S-channel production of stops. And so this situation, if we don't see anything, will start to become worse. Okay, so that's what's strictly needed. All right. let me talk about these sort of first order, not zeroth order. At zeroth order, the MSSM looks spectacular. All the problems begin at first order, and something that probably many of you know, especially those of you who worked in model building know, but maybe is not as widely known as it should be, is there's maybe a little bit of a sense that people in this business thought it was totally obvious we're going to be seeing supersymmetry at the LHC. Obviously, yes, everything is going rah-rah, gangbusters, great. And then the LHC turned on, we didn't see superpartners, and all of a sudden now we're worried, okay? And nobody who has thought about this problem with any depth over the last 10 or 15 years thought that way, okay? And no one said that. In fact, it's rather the other way around. I think at least to me, the state of affairs is I'm not today, right now, particularly more worried about low-energy supersymmetry than I was before the LHC. Mostly what the LHC has done so far is rule out some loopholes, which I couldn't imagine populating from the top down anyway. But the loopholes are closed. So the reason I'm not more worried about it now, particularly now, than beforehand, is that I was already quite worried ahead of time. Okay? And there are already reasons to suspect there was something a little wrong, not necessarily humongously wrong, but a little wrong, enough that you stay up at night wondering, okay? And so why? Why did we think something was wrong? And, it's many people were saying these things. There was the sort of this infamous little hierarchy problem. Barbieri and Strumia called it the Lepp paradox. There's many aspects to it, but I want to focus on, so the usual way people talk about it is that there's some degree of tuning associated with electroweak symmetry breaking, even in Suzie, maybe 10%, 1% level tuning in any of the sort of nice top-down theories that people wanted, that the people considered. But I just want to spend a second telling you about how I think about the problem, because it's not so much this numerical level of tuning as a sort of more structural thing about what the spectrum looks like. So the real problem with Suzie, this first order problem, is not why no Suzie at the LHC. It's not that. There's why no supersymmetry at LEP. And it's not even that. There's why no supersymmetry at a machine that maybe none of you even have heard of called Petra, that came even before that, okay? Supersymmetry could have shown up already long ago, and from some point of view, it should have shown up long ago. So let me explain why that is, just qualitatively. What should the supersymmetric spectrum look like? Just if you're very naive. If you're naive, this is the naive Suzie spectrum. The naive Suzie spectrum should have colored particles, squarks, gluinos, and so on, heavier than uncolored particles, leptons, electroweak Inos, and so on. For the well-appreciated standard reasons that the renormalization group tends to make colored things heavier than uncolored things. Okay, but there's a very significant guy missing here, which is what about the Higgs? The Higgs is uncolored, but as you know well, and as we've seen already the effect in other places, the biggest dimensionless coupling is actually the top Yukawa coupling, and the top Yukawa coupling mixes up the Higgs with the stops. So you would expect that the stops are up around here. Well, the stops are here, so you'd expect that the Higgs is up around here with the squarks and the colored guys, for that reason, because the top drags it up to where everyone else is. And now the mass squared for the Higgs is directly what's setting the Z mass. So you'd expect that the W and the Z are up here, okay? So that's the sort of naive spectrum. When I said people expected Suzie at LEP, These are not the theorists who for 30 years are telling you that supersymmetry is around the corner 6 months from now, okay? These are the people who give, at least our part of the subject, a really bad name. They're the people who keep moving the goalposts, and they think you're going to forget what they said 6 months ago, right? But it's not those people who are optimistic about supersymmetry at LEP. It was much more sober and serious people who were optimistic about Suzie at LEP, and it was for this reason. So if you look at papers back then, you know, you look at Suzie papers today, all the spectrum is up at a TeV, 2 TeV, things like that. Back then, all the talks, all the papers were, you know, 40 GeV for 45s, 50 GeV for sleptons, 200 GeV for stops, you know. And it wasn't because they were wildly optimistic, it's because of this basic picture. This is a theory to explain the naturalness of the electroweak scale, right? The W and the Z are not at 2 TeV, they're at 80, 90 GeV. So also super naively, you would expect something like this to be true, but in a little more detail, you'd expect the Z to be closer to the top of the spectrum, and the Higgs to be closer to the top of the spectrum, and to have other guys lighter than it. So this is the theorist's natural spectrum. The problem we have on the other side is that what we've actually seen now are the Z, and now we've seen the Higgs, and God knows where everyone else is. Okay? And as I think Nazi also made this joke, we have the tension between the natural spectrum and the natural spectrum. Okay? What? Let me draw this picture in yet another way. All equivalent ways of saying the same thing, but this is the way in which the percent tuning or worst way of talking about things is highlighted. You've all seen this picture in the MSSM where you start at some high scale, maybe scalars are all comparable to each other, and the Higgs mass squared goes negative. Right? The Higgs mass squared under the normalization group goes negative somewhere. It's nice that it goes negative somewhere. That by no means means that the electroweak symmetry breaking is guaranteed in Suzie. It's just one nice ingredient that might help. Remember, there's a mu term, which just gives you a big positive contribution anyway, so you're always balancing against something positive against something negative. The statement that supersymmetry predicts electroweak symmetry breaking because of this effect is simply wrong. But anyway, it's a true fact that this is what the soft terms look like. This is what the Higgs soft mass looks like. And often, especially when you're just first starting out as a student, you think maybe there's something very important about that scale where it crosses 0 as you run the RG. There's some scale where it crosses 0, something exciting, some exciting physics is happening there. Maybe that's what's going to set the VEV of the Higgs or something like that, just very naively. And then you're told in your courses, no, that scale where it crosses 0 has nothing to do with anything. There's nothing important about the scale where it crosses 0. You really have to keep running the renormalization group from the high scale roughly to the mass scale of the particles, you know, the TeV or whatever, and that's where you compute the effective potential or whatever you want. So, you know, this is what you would have thought it looks like. There's one scale here where it crosses 0. There's the overall mass scale of these guys, you know, hundreds of GeV. So there's the 100 GeV scale. And these two scales, once again, have nothing whatsoever to do with each other, right? After all, what determines the scale where this crosses 0? This is just some accident of the dimensionless ratios of soft terms in the ultraviolet, right? You're running the RGEs. The overall mass scale of the soft masses in the RGEs is totally irrelevant. You can scale it out. And there's just something to do with the dimensionless ratios and the top Yukawa coupling and maybe other things, but it's just some fact about these dimensionless ratios that sets where that scale is. It's no deep meaning. And then there's the overall scale of the masses themselves. Where's that coming from? It's coming from some Suzie breaking sector and mediation and all the rest of these things seem to have nothing whatsoever to do with each other, right? All right, and that's the picture that would lead you to make this kind of prediction, after all, right? This is telling you, if you do nothing else, Just the RG evolution drags the Higgs mass to be comparable to what the stop masses are. That's what's setting the overall scale here. So if you're at this picture, what is the Higgs mass going to be compared to the stop mass? Something order 1. Well, unless it just so happens that the scale where it crosses 0 is like right around that scale. Within like let's say you wanted to make the Higgs mass squared 10 times smaller. Let's say you want to make let's say the stop is at a TeV. You wanted the Higgs mass squared to be at 100 GeV. Then maybe, it sounds crazy, but for some reason, the overall 100 GeV scale would have to be within a third of an e-folding of this other scale, where that was determined from these dimensionless ratios in the UV. Okay? That's the picture that would need to happen in order for the Higgs mass to be significantly different than what the stop masses are. Okay? The difficulty is that's what we have to live with if we want, at least in the simplest pictures, if we want to have supersymmetry at the weak scale. In order to invert this picture and put the Z and the Higgs at the bottom of the spectrum, we have to imagine that these two scales that have nothing whatsoever to do with each other ended up within a third of an e-folding of each other. Okay? And that's one way of talking about this percent, or by now more like a 10 to the minus 3 level tuning that you have in typical theories that have an ultraviolet life. Okay. Now, in the MSSM itself, there is a somewhat milder cousin of this problem, which is just the difficulty in getting the Higgs mass heavy enough. As Nati reviewed, at tree level, we expect the Higgs to be lighter than the Z. By the way, there's a very good reason for that. Why should the Higgs have anything to do with the Z at all? Of course, we can look at the actual supersymmetric Lagrangian, and it's clear the quartic coupling is set by the D terms are set to the gauge coupling related to the Z mass, but it's also related to supersymmetry itself. Because if you just think about the spectrum, imagine you broke supersymmetry. Imagine you broke electroweak symmetry in a way that was actually supersymmetric. If you broke in a way that was actually supersymmetric, we have a problem, because we have, let's say, the Z particle, which has 3 degrees of freedom, but its superpartner would be the Gino, would have 4 degrees of freedom as a fermion, right? So what is it that matches supersymmetric Bose-Fermi? There's got to be one extra scalar field, massive scalar field, whose mass has got to be the Z mass, right? That's the Higgs. So if you broke electroweak symmetry supersymmetrically, the Z and the Higgs are related. So it's not some sort of accident of factors of 2, and maybe it could have been root 2 times that. No, I mean, it's sort of deeply related to the fact that supersymmetry is, that the Higgs is like the partner of the Z as far as electroweak symmetry breaking is concerned. And in more detail, at tree level, it's actually got to be lighter than the Z. And that has to do with the fact that in supersymmetric theories, we can actually easily have flat directions. So it's easier to make it lighter. It's possible to break electroweak symmetry without even having any restoring potential along the d-flat directions at all. But it's hard to imagine making it heavier. OK. Of course, we can make it heavier because supersymmetry is broken. And so the Higgs mass is less than or equal to mz. But there are corrections that come from Suzie breaking, dominantly coming from the stops. Actually, this is a bad way of talking about things. Okay? So really, imagine that we have, as we said, it's Suzie that makes the quartic coupling equal to g squared. The Higgs quartic coupling equal to g squared. But after we've broken Suzie, there's no reason for that relation to be true anymore. And in particular, in the low energy theory beneath the stops, there's the same old one loop diagram contribution to the running of the quartic coupling from the top quark that we talked about in the first lecture that run the other way in the standard model is associated with the vacuum instability. Okay? Exactly the same thing, now going from high to low energies, adds to the quartic coupling of the Higgs. Okay? And it grows quadratically with the top Yukawa, so this is a big effect. This can be a big effect. So it goes in the right direction. It makes the quartic bigger. It makes the Higgs heavier. But it's making the quartic coupling heavier logarithmically as you make the stops heavier, okay? Just because it's a running effect. So it's making the quartic bigger logarithmically, and we're making the fine-tuning worse quadratically as we make the stops heavier. So that's why every few GeV that you, every 2 or 3 GeV kick that you give the Higgs mass, you're doubling the price in tuning. Okay? So, and this is why, you know, already when the limit from LEP was that the Higgs was 115 GeV, this was already what was starting to get people somewhat concerned. If you want to just take the MSSM and get the Higgs up to 115 GeV, then naively you need stops around a TeV for this log to be big enough. And stops at a TeV is already making things pretty tuned. Okay, so that's the 10%, 5%, something like that. So, of course, there's all sorts of variations of the MSSM, and all you need, I mean, in all cases you need Suzie breaking for a variety of reasons, but it's possible to make the Higgs heavier. It's possible to make the Higgs heavier. You can add a singlet like the NMSSM. You can imagine there's some extra U1s, and the extra U1s give additional D terms for the Higgs, and if Susie's badly enough broken, even when you integrate out the U1s, you get an additional kick to the quarter coupling of the Higgs. And so the status before we knew the Higgs was 125, but when we knew the limit was 115, is that you would either have to tolerate this sort of stops at a TeV and 5%, 10%, that kind of tuning minimally, or you could add a little dipsy doodle, add a singlet, add a U1, something like that, and then still everything is fine. So the bottom line for what we learn when we take the Higgs from 115 to 125, where it's actually found, is that now we have to have stops at a TeV and a dipsy doodle. Okay? So an extra singlet, U1, something like that. So that extra 10 GeV does affect things a little bit. It makes it still more elaborate what you'd have to do in order to explain it. But already, you see, already the first, completely independent of supersymmetry, just the broad idea of naturalness is being put under tension, not a humongous deal, but under some tension from the fact that we haven't seen anything at the LHC. In the particular context of supersymmetry, the absence of stops and gluinos is pushing us into the 10% tuning territory already. And so the fact that to accommodate the 125 GeV Higgs, we need an extra dipsy doodle on top of what we imagined before is just par for the course, given this state of affairs. Okay? So that's, now, let me let me tell you my own feeling about this. I think people, including me, but definitely not just me, have spent a long time trying to still find a perfect supersymmetric theory. Okay? Maybe we have some tension now already from the fact that the stops are a little heavy, but ignoring that really solves all the problems. It's totally natural. The Higgs is heavy enough. And it's a really interesting set of problems for a model builder, because if you enumerate them, the sort of supersymmetric theories have 4 or 5 sets of difficulties that you want to solve. And it's easy to solve 4 of the 5 problems. Okay? And easy and natural and nice. You want to solve the flavor problem, no CP, all of this stuff, cosmology, okay, you can go down one way, but it's pretty bad for naturalness. Or you come back and you try to make it more natural, then it's bad. It's just like one of the carpets that you try to fit in a room, and you keep tutting on the end one way or the other, and it's the carpet's too small or too big, but you don't know when you're in one corner or the other, constantly pulling on it, trying to make it work. It's still possible that something like that is out there. I think that would be one of the most interesting things if we actually, of course, not only would it be euphoric that we discover this whole panoply of particles at the LHC, but if it really is natural, there's probably something that we missed. Because, as I said, there's like dozens and dozens of people have spent 10, 15, 20 years of their life looking for some mechanism that would explain it, and we've all failed. But we could have just all missed something. And if we actually, you might find it before the experiment turns on, or if we actually see these particles, we might discover what that mechanism is. So that's possibility 1. I give that, it's pretty reasonable. I don't think it's unlikely that could happen. I mean, all of us would kick ourselves a lot for missing it, but that's no reason to think it won't. Possibility 2 is that it'll just be percent tuned. The stops will be there at 1.5 TeV. There will be 1 TeV, you know. We'll see half of the superpartners, the other half will be a little heavier. It'll be a percent tuned, right? And if you ask me, compared to at least all of my own efforts to find a spectacular, nice, natural theory, by the time you go through all the model building gymnastics in order to make it happen, and then you look and you say, could it just be a percent tuned instead? It's very hard to quantify what I'm about to say. It's very hard to quantify the sense of tuning in model space, the clever cost, okay? It's hard to quantify it. I can tell you about extremes. For example, I think the likelihood that little Higgs theories describe nature is very close to 0. And the reason they're so unlikely is that they're extremely clever. They're ingenious. You pick that group, and you break things here and that and the other. And it just seems so unlikely that that's the way the world works. I mean, I worked on these theories, and I worked on them with Ann Nelson, amongst other people, who's maybe one of the most talented model builders in the world. And I just told Ann one day, you know, the problem is that God is not as clever as you are, right? And it just seems, it seems implausible. I mean, so I think I would be shocked if little Higgs theories are right. Not because the broad idea is fine, the broad idea is great, actually. It's a good broad idea, but that's what I was saying in the first lecture. Broad ideas can be fine, then you try to really make them concretely work, and then you find these things. You find these things that just make it smell and feel wrong. Little Higgs theories smell, they stink to me. So that's an extreme of way too clever, okay? But compared to that, at least my own efforts in supersymmetric theories were not as badly clever as that, but they were still too clever. And if I had to bet, is it going to be clever like that or just percent tuned? I would take percent tuned at the moment, any day, okay? And why? Well, we've seen percent accidents in nature. The moon eclipses the sun, that's a percent accident. We've seen all sorts of little accidents elsewhere, nuclear physics and so on and so forth, right? So that could be what's going on. I think that's plausible. That's very, very plausible. And if it happened, let's say it stops at a TeV and it's all like that. Then, of course, 0th order, it's super euphoria. No one will talk about naturalness for 10 years. No one will care about it. We'll have all the fun in the world exploring the superpartner spectrum. And maybe in 10 or 15 years, people will come back and say, that still looks really weird, right? You start putting it in the textbooks. We have this spectacular natural theory that explains that this is what it looks like, right? And then when the student puts up their hand, why do those scales end up on top of each other? Don't know, just happened. That's just the way it is. But, so it's possible, but I think eventually it would start bothering people again. Not for a long time, but eventually start bothering people again. So that's my 2 cents about the natural version of supersymmetry. But also, in this natural version of supersymmetry, that's what I was telling you before. We have these opposing hints from what we've learned so far. Unification, dark matter, all this stuff, naturalness, Suzie is fantastic. Why haven't we seen anything? The cosmological constant, where are the particles are pushing in the opposite direction? And if any of the scenarios I just told you was right, a mechanism or percent tuning, some of those clues will have just been not important. They've just been misleading, right? You'd say, okay, the ones that said to worry about things, why I haven't seen anything, it wasn't a big deal after all. Or it's just percent tuned. It didn't have a good answer after all, okay? In either one of those things. So what I now want to talk about is the picture in which everything we've seen so far makes sense, okay? Makes sense and is, and all the hints were actually correct, but some of them were misread, okay? And that's the picture of split Suzie. And as I said, it definitely does not mean that it has to be correct, but it's the only picture I know of in which all the things that happened in the last 30 years have a purpose. Oh, actually, before going on to that, though, I want to say one more thing about actually 2 more things about Suzie. three more things about Suzie. First of all, this little hierarchy problem, the problem that why wasn't the z near the top of the spectrum? Why did it end up being at the bottom of the spectrum? This thing, which is associated with percent level tuning or whatever we're talking about at the minimum, okay, that was handed to us by LEP, essentially, by the failure to discover superpartners at the 100 GeV scale, right? And we talk about it at length. That problem is actually associated with another interesting tuning in supersymmetric theories that's not as universally talked about, but is there, and is associated with one of the other spectacular successes of the early 90s, which was and earlier than that, which was that WIMP dark matter can work, okay? So you all know about the WIMP miracle. If you don't, we'll have nice lectures about it. It's not quite as miraculous as it's made out to be, but anyway, it's pretty good. So again, there was this qualitative thing, yeah, we can have dark matter at the TeV scale. Neutralinos can be dark matter. But in a little bit more detail, neutralinos could be naturally great dark matter candidates before LEP, but not after LEP. After LEP, getting the right relic abundance itself took another tuning of the percent level or so. Okay? Why is that? Well, think about who the dark matter could be in supersymmetric theories. It's the LSP, right? And let's, for the moment, take a limit where we imagine the LSP is pure. So it could be a Bino, a Wino, or a Higgsino, right? They're all WIMP miracle, roughly speaking, but again, a little more detail. If it's the Bino, and if we want all these particles to be light, right? Because it's supposed to be natural, so all these particles should be in the hundreds of GeV. Then the problem is if it's hundreds of GeV, and you're looking for a thermal abundance, if it's Higgsinos or Winos, you get way too little dark matter if they're down at hundreds of GeV. Okay? They annihilate with each other very efficiently just through the standard model gauge interactions, and so the relic abundance we get is tiny from them. That's one way of talking about how unconstrained the WIMP miracle is. If you just say you want a dark matter particle just annihilating through the standard model gauge interactions, what would its mass have to be? The answer is its mass would, if it's a doublet, it'd have to be 1 TeV. If it's a triplet, it'd have to be 2.5, 3 TeV, if you want to just get the right relic abundance. So that's very bad. If that's the bottom of the spectrum, there's no way the theory is going to be natural, right? So if you want the bottom of the spectrum to be much lighter, it can't be a Wino or a Higgsino. But it also can't be a Bino, because pure Binos don't interact at all, and you'd get vastly too much of it. Okay? They don't annihilate at all, you get vastly too much. So the problem is that if it's fairly pure and these states are light, you either get 100 times too little dark matter or 100 times too much dark matter, if it's Wino or Higgsino on the one hand or Bino on the other. So what you needed for it to work nicely was a good mixture, right? You just wanted the Winos, Higgsinos, Binos to be all mixed up with each other. Very, big amount of mixing, so you could sit halfway between them. And when you could not naturally easily get the observed relic abundance that we get, that's the place in parameter space where it works. Okay? The problem is that after LEP, not only do we discover superpartners are heavy, but by moving everyone up, it means the electroweak symmetry breaking contributions to their masses are getting smaller. So it's more likely that they're pure states. And then we're back to this problem, right? Because they are pure states, you naturally get 100 times too much or 100 times too little. And that's why when you look at the plots in various simplified MSSMs for where you are to get the right relic abundance, you get these tiny little thin slivers. The slivers aren't so tiny because that's the range of the observed value for omega from dark matter. It's because you're living on an edge. If you go one way or the other, you tend to get too much or too little dark matter. Okay? So this is a dark matter counterpart of the little hierarchy problem we were just talking about for electroweak symmetry breaking. Exactly the same thing electroweak symmetry breaking infects dark matter and means getting the right relic abundance also takes a tuning. Okay. Okay. Secondly, okay, I'll get to that in a second. So sorry. Okay. so that's all I want to say about normal Suzie. So, so I think, just to say one more time, the most important thing to take away from what I said, though, is that regardless of any feelings, we have there's this bullseye for what we actually must see at the LHC, and if we don't see it in the next run, then I think there's no ifs, ands, or buts about whether supersymmetry or any other natural explanation is actually not somewhat fine-tuned already. Okay, so I don't have that much time left, so I don't want to spend too long on the philosophy of anthropics and the multiverse. But I just want to say that, of course, the cosmological constant is the biggest elephant in the room. And we only have, as of today, we have oh, by the way, not only is it the elephant in the room, but as we also said last time, if you apply the naturalness philosophy to the cosmological constant, you just make an incorrect prediction, that there should be new physics at the millimeter scale. There's no new physics at the millimeter scale, with apologies to Raman, who will talk about, probably not here, but has talked about potential caveats to this, but there's certainly... Oh, great, fine, great. But just to drive the point home a little bit, imagine that that there are other creatures in our universe made of atoms whose size, their atoms were 10,000 kilometers big. So they're humongous creatures, right? They're very big creatures, but they know about physics. They discover the accelerating universe. Well, they know about physics. They discover the cosmological constant problem. They see the universe is accelerating, so they even have a measure of the size of the cosmological constant, and they wonder what could possibly solve this cosmological constant problem. And they think, and their most brilliant theorists come along and say, supersymmetry. Supersymmetry could solve the cosmological constant problem. And it could. And you'd need to have supersymmetry at the millimeter scale. Now, millimeter is very hard for them, but they build the Large Millimeter Collider and looking for supersymmetry. It must be there, right? You know, what else could solve it? They don't even have any of the other possible solutions. There's no supersymmetry at the millimeter scale, okay? But the cosmological constant problem could have been solved by supersymmetry, and it isn't. Oh, this is the small comment I wanted to make, though, is that since we're talking about the cosmological constant, this is something supersymmetry has over every other approach to the hierarchy problem. Supersymmetry is the only picture we have that even in theoretical models, in toy universes, addresses qualitatively this question of why there's a macroscopic universe, okay? If you want a macroscopic universe, as we said, the first thing you need to have is a small cosmological constant, and supersymmetry is the only way we know of guaranteeing that, okay? So that perhaps also explains its ubiquity and why so many people run into it when you try to, for example, build consistent theories of quantum gravity. If it's worth its name, if it should be called gravity, it should have a flat space with things running around, banging into each other, and so on. So you have to have a zero cosmological constant before even getting started. And supersymmetry is the only thing that we know that does that. So in a sense, supersymmetry is the only mechanism we know to make a macroscopic universe easily, okay? And I think that explains why we keep running into it all the time. People who talk about ways of doing gravity without saying the word supersymmetry, you should always ask them, where's your big universe, right? Do you really have can you have planets and things orbiting around and stuff like that? Typically they can't, they don't even talk about it. And if they don't talk about the cosmological constant and they haven't said supersymmetry, they're probably crackpots and you should stop talking to them, okay? But anyway, that explains why one of the very deep things about supersymmetry is the only thing we know that even theoretically gives you large universes. What we're talking about now, all of this belly aching now, from the Planck scale point of view, could be just very fine details, right? Whether you generate a scale at 100 TeV or 1 TeV, you know, these are all so gargantuan compared to the Planck scale. So it could very well be that we just get a big head start on making any of this possible by having supersymmetry at low energies at all. Okay, so that's an important point I should have made right at the start. Okay, but given that even supersymmetry leaves us at least 60 orders of magnitude, if not more, to go with the cosmological constant, the only scientific explanation we know of today is Weinberg's explanation. anthropic explanation, environmental explanation, for the smallness of the cosmological constant. And I'm sure you all know what it is, that you imagine this gigantic multiverse, the constants taking on different values. By the way, sometimes people say the laws of nature are different from place to place. I think that's not a good way of saying it, because the whole point is that there's one actual set of laws of nature. It's not that elsewhere in the other universes apples fall up. You know, there's actually one underlying theory, but it could be consistent with that one underlying theory. We have tons of realization, and it's just the constants that change from place to place. The constants don't necessarily have to reflect something deep about the laws. The laws could be unique, but the constants change from place to place. Apples fall everywhere in the multiverse. But anyway, there are so many of them that in most of them the cosmological constant is big. In those regions, the universe is blowing itself apart, accelerating, and no structure can possibly form. Those parts of the multiverse are just empty, and only in some tiny sliver regions, accidentally, there are so many vacua, these fine-tunings just happen accidentally, but those are the only places that will have any structure. And so it's not surprising that we find ourselves in one of those pockets of the multiverse. Much like it's not surprising that we find ourselves on planet Earth rather than in the middle of interstellar dust, interstellar space. There's 60 orders of magnitude more volume in our Hubble region in interstellar dust than on planet Earth, but it's not a pressing problem of theoretical physics that explaining that 10 to the minus 60, obviously we're going to live on rocks and not in the middle of nowhere. So that's the style of explanation. You could ask, could that explanation be, something like that explanation work for the hierarchy problem? And for this sort of explanation to work, at least in any reasonable seeming way, you can't apply it to completely random questions. In fact, you have to have a certain character for the quantity that you're trying to explain. The quantity you're trying to explain needs to have the property that if you change it a little bit, you dramatically destroy something about the long-distance properties of the world, right? So, and furthermore, there's some indication that it might be the explanation if the quantity that you're talking about is close to a dangerous edge, where it's close to the place where the world would change radically, right? I mean, if Weinberg says the cosmological constant has got to be this, and you measure it and it's 10 orders of magnitude smaller than that, 50 orders of magnitude smaller than that, then, well, that's obviously not the explanation, right, for why the cosmological constant is so small. On the other hand, what he actually said was that he was writing this paper to falsify this idea, that it should make a prediction that you find the cosmological constant pretty close to this dangerous value, and that when it's not seen, this idea can be put to rest, and of course, exactly the opposite happened. So we can ask, could that be true for the Higgs mass? Actually, just even before getting to the details of what it could be true for the Higgs mass, let me say that the parameters of any theory that are most amenable for this kind of explanation are exactly the relevant operators, okay? It's exactly the flip side of what gives you the fine-tuning problems to begin with. That's the point, after all. These parameters are such that small changes in them make huge changes to the infrared physics, right? So it is interesting that the biggest, most relevant parameter we have, the cosmological constant, is explained in this way. Now we can ask whether there might be a similar character explanation for the Higgs mass. And there is. It's not remotely as dramatic as Weinberg's explanation, but there are various accidents about our world that seem very important for our existence, very gross things about the world, which seem to be accidents in our current understanding. So, for example, our world has many complicated, nice atoms, and that's important for a whole variety of reasons. Why do complicated atoms exist? In fact, that's a very naive question that you could have. Why do we have any atoms other than hydrogen at all? After all, the neutron is unstable. You take a neutron in empty space, it decays in 15 minutes. So why do we have atoms at all? And the answer is, well, it's because the nuclear binding energies are comparable to the neutron-proton mass splitting. If that wasn't true, there would be nothing other than hydrogen, right? Let's say the mass splitting between the neutron and proton was much bigger than nuclear binding energies, then obviously there would be nothing other than hydrogen. So why are the nuclear binding energies comparable to the neutron-proton splitting? It's just an accident. Those things are set by two different pieces of physics. And in fact, if you imagine, just as a mental exercise, you take the Higgs web. Just imagine you took the standard model, you change the mass squared of the Higgs, you make it more negative, more natural, say. Then the down quark gets even heavier than the up quark. And already within a factor of 3, as you make the Higgs valve bigger by a factor of 3, the down quark gets so much heavier than the up quark that the neutron becomes so much heavier than the proton that the neutron-proton mass splitting exceeds nuclear binding energies. There's nothing other than hydrogen in the universe. Okay? So that's very interesting. Okay? So if we take our two relevant operators in the standard model, lambda and m Higgs squared, okay? What we're saying is that there's this Weinberg value here, call it structure. There's this value where you have atoms, plural, okay? Naturalness would lead you to suspect that that you go this way or that way. And what we actually see is something very close here and very close there, right? So this is just a fact, right? How we interpret it is up to us, but if you start thinking along the lines of a multiverse, then this is, again, it's not remotely as impressive as that, but it's not an implausible argument for why this might happen. Well, let me say it another way. Let's say you believe there's a unique vacuum. All this stuff is crap. There's a unique vacuum. Everything is great. Everything is what it is. Then this is just some curious fact about this unique vacuum. Huh, look at that, right? Oh, what a coincidence. That's funny that it happens that these numbers are so close to these places, which would dramatically change what the world looks like, right? All right. So this is, if you like, we had our two tensions pushing in opposite directions. The naturalness arrow, which leads you down the first road that we talked about. And now you take these things seriously and say, oh, obviously it's going to be the standard model and nothing else, right? Cosmological constant is anthropic. The Higgs mass is anthropic. There's no reason for anything other than the Higgs. We saw the theory makes sense all the way up to very high energies. So that's the other arrow. You take the other arrow as maximally seriously as possible. And you say, all the other hints that we're on the right track, dark matter. Dark matter could be axions. It has nothing to do with WIMPs. You know, unification is just an accident, right? So these are the two attitudes. You can take the naturalness, rah, rah, rah. All the other hints are just wrong and accidents are not telling us anything. Or, no, naturalness is all crap. The fact that Suzie and unification, everything's in work is an accident, right? Either one could be true. But as I said, there is a picture where all of them are correct and telling us something, and that's what I want to spend my last 15 minutes talking about. Okay. So the picture here is that nature is supersymmetric in the ultraviolet. It's there for deep theoretical reasons. Supersymmetry is giving us this big head start and getting a big macroscopic universe. Okay, all this. Now we just have to ask how supersymmetry is broken. Okay, and I want to take an attitude here, which is again, it's the. And I can do this as a card-carrying model builder, and as I said already, we do a lot of these kind of activities in model building, and we feel a lot we're either being stupid or we're being ingenious, where ingenious has negative connotations. Okay, so I don't want to do that. I want to take an extremely simple point of view. I'm not going to do anything clever. I just want to see what wants to happen. If you start from the top down, just imagine you have some theory, break supersymmetry. If you're just totally dumb, you don't work hard, what is it that wants to happen? Well, something that happens quite generically when you break Suzie from the top down is you can ask, well, so you've broken supersymmetry, so what particles are going to get a mass? Of course, the only symmetry protecting the scalars is supersymmetry. So scalars should get a big mass. But what about the fermions? What about gay Ginos? And Higgs-Ginos we'll talk about in a second, but what about gay Ginos? Well, the gay Ginos may be up there with the scalars, but it's true that you need to do a little bit more to give the gay Ginos a mass. They're fermions. Chiral symmetries are protected by an R symmetry, so you have to break the R symmetry too in order to get the gay Ginos a mass. So just that makes it at least plausible that you could have a splitting between the scalars and the gay Ginos. We're not talking anything about phenomenology. We're not talking about, the real, just you break Suzie, and it's easy for scalars to pick up a mass, and you have to work a little bit more for the gay Ginos to pick up a mass. This is actually substantiated in actual theories. Okay? So in many actual concrete top-down theories that break supersymmetry, this just happens. It happened to people in the early 80s when they started building concrete supersymmetric models. And again, what was people's attitude? Not a problem, an opportunity. Say, no, there's something a little more interesting Suzie breaking sector. We have to have the gay Ginos and the scalars at the same place, otherwise it's not natural, and so on and so forth. Definitely not impossible, easily possible. But if you just want to be as dumb as possible, then it's certainly easy. Maybe I won't say it's easier, but it's certainly very, very easy to have it be the other way. And in fact, in the more sort of modern ways of thinking about what Suzie breaking happens, you break Suzie in some hidden sector, and it's just mediated to the standard model. R symmetry definitely has to be broken. Okay? We have to break R symmetry. If we don't break R symmetry, we can't cancel the cosmological constant after we break supersymmetry. So it's not a question of whether the gay Gino mass are going to be generated. They will be generated. It's really the gravitino mass is the order parameter for R symmetry breaking, and the gravitino has got to be massive. But and so you would expect, the gravitino is getting mass from Suzie breaking suppressed by the Planck scale. The scalars, unless you do something unless you make some arrangement or you're clever, the scalars should be at least where the gravitino is. It's hard to get things more weakly coupled than gravity, okay? So the scalars and the gravitino should be around each other. But what about the gay Ginos? And if you don't have sort of direct interactions between the Suzie breaking sector and our sector, then the gay Ginos pick up a mass at one loop through anomaly mediation. There's various ways of talking about what it is, but there's a calculable contribution to the mass of the gay Ginos that goes like alpha times the gravitino mass. Okay? So in this very simple picture, top-down breaking Suzie, you naturally get a one-loop splitting between the gravitino and the gay Ginos. Familiar from anomaly mediation. But what about the scalars? Well, you'd expect the scalars to be up where the gravitino is, maybe heavier, because they might be more strongly coupled than gravitational to Suzie breaking. And in fact, the two sets of papers on anomaly mediation that were written in the 90s, one by Raman and Lisa, and the other by the CERN group, they both have this picture of gay Gino masses, and on top of that, Raman and Lisa had this extremely nice observation about maybe hiding the scalar somehow from Suzie breaking, sequestering, giving a reason why the scalars might also be lighter than might also be at the same scale as the gay Ginos. The CERN group didn't have this, and so they were apologizing in their paper all over the place. Well, too bad. It would have worked great, except the scalars are too heavy. Okay? They actually tried to make excuses for the scalars to be as light as they possibly could back then. But anyway, so again, part of the not a problem but opportunity attitude. But if you don't sequester, if you don't make any extra arrangements, then the scalars are heavy, the gay Ginos are light. Just break Suzie in a hidden sector, no special arrangements. That spectrum just wants to happen. Okay? And most people's attitude was the spectrum wants to happen, but it's bad for naturalness. And the attitude that we now want to take is that it wants to happen, so let it happen. Okay, so the idea is now that we have, because it's a loop factor, we have scalars at hundreds to thousands of TeV, and the gay Ginos at the TeV scale. So now what is it that sets the bottom to be at the TeV scale? The second we have this picture, especially if we're going to imagine the scalars are heavy, then naturalness isn't the guiding principle anymore. And we just say, yep, it is not the guiding principle anymore. It's not very wrong. Again, from the Planck scale point of view, compared to numbers like 10 to the 120 and 10 to the 30, this is chump change. Okay? This is maybe a part in 10,000, a part in 100,000, a part in a million, at most extreme level of fine-tuning. From the point of view of naturalness, it's horrible. But from the other point of view, where you imagine there's this big multiverse and whatever the notion of statistics or measure is, I have no idea what it's supposed to be. I'm just making the naive claim that 10 to the 120 and 10 to the 30 seem like much, much bigger deal than a part in 10,000 or a part in 100,000. So this could be, as I said, chump change from that point of view. Okay? But if it's not going to be natural, what is it that's telling us anything is going to be down at the TeV scale? And something that motivates having these guys light is if we have R parity as a good symmetry, and we can talk about why you even need R parity if the scalars are going to be heavier. But given my time, let me defer that. There's good reasons why even when everything is heavier, you would need to have R parity. But if you do, the bottom of the spectrum is still stable. And whether you want it or not, whether you want it to be dark matter or not, if everything gets too heavy, you get way too much dark matter, right? And a universe with way too much dark matter, again, looks dramatically different than the universe that we have. So whether or not you want it to be a relic or whatever it is, you don't want to make the bottom too heavy without, again, causing the world to look very different than what it looks. So the bottom of the spectrum is being driven by dark matter in this picture. It could be all the dark matter, it could be part of the dark matter, half of it could be axions, more of it could be axions, but the thing that's pushing it from dragging everything up to very high scales is dark matter. Okay. Now, the amusing thing about this loop factor splitting, putting those scales at hundreds of thousands of TeV, is, so tuning, very bad, okay? Maybe not horrendous, but very bad. But then all of the concrete problems with the MSSM, FCNCs, CP, all the cosmological problems that people talk about, all of these things are just gone immediately. So it is interesting that the things that gave us the concrete problems were the scalars. Okay? Not the fermions. If the fermions are light, everything is fine. I haven't talked about the Higgs-Inos. I'll talk about the Higgs-Inos in a moment. Okay? So already that's phenomenologically interesting. What about gauge coupling unification? Well, something that you may know, so let's go back to that supersymmetric picture of unification. It's a very simple fact. Probably most of you know it, but if you don't, you can ask who's important? Which particles are important to make that picture of unification work? We're changing the beta function compared to the standard model, right? So what are the important particles that are being added? We're adding all these superpartners, also the superpartners of the gauge-Inos and the Higgs-Inos. And so is it the whole picture that everything is important to change that? And the answer is the only things that are important are the gauge-Inos and the Higgs-Inos. In fact, the Higgs-Inos most of all. And it's a very simple reason that if you add any complete multiplets of SU5, any vector-like particles that are complete multiplets of SU5, they don't affect the picture of unification at all. The simple way of seeing that is to imagine that those three lines are three runners, right? They're all running, and they all hit at a point. So jump into the frame of reference of alpha 2 inverse. So alpha 2 is sitting there, and alpha 3 and alpha 1 are running towards them, and with their ratio of velocities set such that they magically hit at the same time, right? So that's the wonder of unification. Now, let's say we add particles that are in multiplets of SU5. That just increases by the same amount the slope of this line for everybody. So when you jump into the frame of reference of alpha 2, nothing changes. Those relative velocities are all the same, and so you don't change the fact that there's unification. So complete multiplets of SU5 are totally irrelevant to that picture. Of course, if you add too many of them, you might hit a Landau pole, but the fact that those lines cross is totally insensitive to complete multiplets of SU5. That means that all of the standard model fermions are irrelevant, all their superpartners are irrelevant. The only things that are relevant, ironically, for the picture of unification to work are the non-unified multiplets. So the gauge fields are important themselves, of course. If you just add gauginos, then it's also easy to see. Remember the standard model? Kind of unified, but not quite. Imagine you took the MSSM, you forgot about everything, but you added the gauginos. Then you'd get exactly the same picture as a standard model, but just rescaled. Rescaled in energy. And the reason is, again, if I jumped into the reference frame of alpha 2, I'm just changing the gauginos and the gauge fields. Their beta functions are actually different. But all I'm doing is, while I'm changing the actual size of the velocity, the ratio of the two velocities is fixed. So they just go a little more slowly, but they still meet or don't meet as well as they did before. So actually, with just the gauginos, you get unification pretty much as well as the standard model, but just the picture gets rescaled. In fact, early on, there are papers saying, oh, we don't really know about this whole MSSM model, we don't care, let's ignore the Higgs-Inos, let's just look at the running. And back then, in the early 80s, the standard model unified pretty well. And then when you add the superparticles, it made it unify at the Planck scale. So they're like, wow, that's just really amazing. It's unifying at the Planck scale. Yet another example of why it's good to always, in model building, be as detailed as you can possibly be and not just leave it at some blah, blah level, because you need the Higgs-Inos. The Higgs-Inos change the story in a very important way. The Higgs-Inos are by far the biggest contribution, much more important than the gauginos, and they change the running significantly. And back then, when the more detailed model builders said, no, let's add the Higgs-Inos, it's an actual model, then you make a prediction for unification that was much worse than the standard model was back then, but that was the picture that was then confirmed by LEP 10 years later. Okay? So the Higgs-Inos are actually the most important particles of all to get unification to work. The gauginos are a little bit, they have some effect. Okay? But in particular, the scalars are totally irrelevant. So we can move the scalars up here and it doesn't change the picture of unification. And finally, so unification is fine. And finally, we can ask where the Higgs-Inos should be. And it's possible that the Higgs-Inos are protected by the same R symmetries as the gauginos, and they could be down here with everyone else. I sort of have the feeling it's more likely the Higgs-Inos are up here with the scalars, because again, you'd have to play some games. You have to talk about some extra symmetry, some structure that would keep the Higgs-Inos light. If you do absolutely nothing, the Higgs-Inos should be where the scalars are. They certainly can't be much heavier than where the soft masses for the scalar are. They can't be too much heavier. If they're too much heavier, then you couldn't tune to make the Higgs light, right? Because they have this humongous positive mass squared from mu. So they have to at least be around where the scalars are, at least as light as that. Then it becomes at least possible to tune the scalars to be light. They might be lighter than that, but my own suspicion is that the Higgs-Inos are probably up here. Now we've pushed the Higgs-Inos up a little bit. So I told you the Higgs-Inos were very important for unification. So does this screw up unification? And actually, it doesn't screw up unification. Those supersymmetric pictures of one loop gauge coupling unification look absolutely perfect at one loop. At two loops, it's a little bit off. Of course, you expect it to be a little bit off because you expect some threshold corrections, both at low energies and high energies, that are important too, and that's why we normally don't get terribly excited about it. But if you ask, what is the supersymmetric prediction for alpha S at mz, at two loops, ignoring these thresholds, it's like 0.128. And the actual value is 0.118. So you need a reasonable threshold correction. Not huge, but some reasonable threshold correction. For example, people talk about having Higgs triplets a little bit lighter than the gut scale as a simple way of doing this. Well, and that has some tension with proton decay and other things, but anyway, it's fine. Well, but that tells you why pushing the Higgs-Inos up is actually going in the right direction. Roughly speaking, pushing the Higgs triplets down is basically the same as pushing the Higgs doublets up, the Higgs-Inos up, and it has the same effect. So it means that the two-loop prediction for gauge coupling unification with this spectrum is just fine. So the alpha S at mz is like 0.115. in this picture if you push mu up with everyone else. So even these little detailed things, to the extent that they matter, they go in the right direction. Okay, so this is it's a simple story. You start from the top down, you break Suzie, there wants to be a split spectrum without working. You're tuning, you're definitely tuning, but perhaps there is indication that there is some tuning given these accidents that atoms exist. We're tuning, after all, humongous amounts of the cosmological constant. But everything else, there's no cleverness. We don't have any of the phenomenological problems, and unification is still fine. All right. So, okay, so if this, and as I mentioned, this idea, this kind of spectrum, as people have run into it for ever since the 80s. You know, everyone and their dog has run into this spectrum, okay? So it's not any, you know, it's not, there's nothing sort of remarkable about running into the spectrum. It's just that it's not so much that people didn't discover this theory. The theory is sitting there since the very beginning, this sort of structure. It's just that mostly people were ashamed of it and tried to not do it. And a number of people in the last 10 years have said, maybe we shouldn't be ashamed of it. Maybe this is the way things actually are. Okay. Now, there's one good reason for taking this picture more seriously now after the LHC, which is that, we discussed a second ago that in supersymmetric theories, the Higgs wants to be near the Z. It wants to be lighter than the Z, okay? And that's what's, it's another way of paraphrasing something Nati says, that it looks like the Higgs is kind of close enough to the Z to smell supersymmetric, but far enough away to smell like there's something wrong, right, in a natural supersymmetric theory. This is not a natural supersymmetric theory, and in this picture, the Higgs mass at 125 GeV is just no problem, okay? In fact, this minimal picture made a prediction. The Higgs mass would be between about 120 and 135 GeV. Okay, not a very sharp prediction, but so 125 is reasonably in the middle of that range. You don't have to tune to go to large tan beta or tan beta very close to 1. You know, tan beta is 3 or 4. The scalars are at 100 or 200 TeV. You just run to low energies, and the Higgs mass is fine. Okay. So, so it's a weak test, but it's the first test that it passed. So, what do we look for? I'll just take 5 more minutes, and I'll end. What do we look for if this kind of picture is right? Of course, we live or die, as far as seeing any of this directly, based on whether we get to produce the bottom of the spectrum at the LHC. Are we guaranteed to make the bottom of the spectrum at the LHC, even if we assume the bottom is all dark matter? Absolutely not. Okay? And this has to do with what I said. Dark matter could be a 1 TeV Gino, could be a 3 TeV Wino. If that's the bottom of the spectrum, we'll never see the top of the spectrum at the LHC. Okay? But it's possible that that doesn't have to be the picture for dark matter. The dark matter could be lighter. It could be that these things are accessible at the LHC. Now, there's one important new piece of information that we've gotten about dark matter. Actually, there's a paper out today on HepPH about this that I encourage you to read. It seems like an important and great paper. That actually tells us that one of the most pessimistic pictures for what dark matter could be in this picture, namely that it's a 3 TeV Wino, thermal relic, a 3 TeV Wino. That's very excluded, actually, already by observations of the galactic center and not seeing gamma ray lines, hard gamma ray lines from dark matter annihilation to photons in the galactic center by the Hess experiment. And and it actually, if you seriously take the constraints from both Hess and Fermi, and you take the sort of middle of the road picture for what the dark matter halo would look like, these authors claim that you more or less exclude Wino dark matter as all of the dark matter, period, whether it's thermal or not, from 3 TeV all the way down to hundreds of GeV. Okay? If you're a little more generous or conservative with thinking about what the halo is, still the very heavy end is just gone. And maybe 1 TeV is okay. Windows around 400 or 500 GeV are okay. But the very heavy end is actually already being ruled out by these indirect observations. And furthermore, future Ayer-Cherenkov telescopes are just going to whomp the whole region. Of course, we'll get to it with the LHC probably first. But anyway, so I really encourage you to read that paper. It's an additional piece of information which at least tells us if it is electroweak charge, the bottom of the spectrum may not be so heavy. It might actually be lighter, which of course makes it more optimistic to see any of these things. Okay, but there's a qualitative feature. I mean, I could talk a lot about signals, but there's one qualitative feature I want to say about the collider phenomenology of these kinds of theories. And that is, especially if the only particles you have down here are the Bino, Wino, and the gluino, even if the Xeno is heavy. So what we could see at the LHC is the Bino, Wino, and the gluino. There's a very simple and interesting fact you can quickly verify for yourself, that if you have particles with those quantum numbers, fermions with those quantum numbers, there's no way they can possibly decay to standard model particles and each other through renormalizable interactions. They don't have any renormalizable interactions at all. The only way they can possibly decay is through higher dimension operators. So this is a very interesting situation because we can produce them. We can, let's say, produce the gluino in this picture, okay? But it cannot decay unless it goes through higher dimension operators. So if we produce the gluino in this picture, then if we see it decay inside the detector at all, we know there's new physics beneath around 500, about 100 TeV or so. The very fact that you see it decay inside the detector would mean that we're sort of like back in the situation like with the weak interactions. Okay, we saw a higher dimension operator finally, right? And it gives us an indication of a scale that's far away, but not infinitely far away. It can't be too much heavier than 100 TeV. And of course, interestingly, this 100 TeV number, this 100 TeV scale, on the one hand, was good for flavor and all the rest of this stuff. On the other hand, was good for getting the Higgs mass to come out at 125. If that scale for the scalars was, was 1,000,000 TeV, the Higgs would come out too heavy. Okay? So the same number is compatible, nicely compatible with the Higgs mass. And also interestingly, the same scale can be probed by looking for displaced vertices from gluino decay. Okay? So we have gluinos decaying. Then if they decay promptly, the scale is less than 100, 200 TeV or so. If you see it with millimeter, centimeter, 10 centimeter scale displacements, then you have indication that the higher dimension operators are coming from that scale. And of course, it's just, it's just tree-level squark exchange. It's just gluino goes to, this is the most plausible thing I can imagine. Bino, for example, okay? That you might have the gluino go to TT bar Bino. So it's that heavy off-shell stop which is being probed by the gluino displacement. So if you see a displaced gluino, it's giving you an indication of where that scale is. And if it's in the range that we're just talking about, also compatible with these numbers, we're not talking about displacements that are so big that it ends up in the detector and it does exotic things like that. It's moderate scale displacements, but it could give us a direct indication of what the next scale is. And as I said, if you don't see displacement, it tells you that the next scale is even closer. Okay? So that's a qualitative thing. These particles can only decay through higher dimension operators. I'm focusing on this one here just for time. There's a displacement associated with that. But even the Winos and the Binos, they can only decay through each other through dimension 5 operators, dimension 6 operators. And that fact that they're only decaying through higher dimension operators has important consequences. For example, the Bino might be heavier than the Wino, but the Bino, again, precisely because it's decaying through higher dimension operators, will never go to leading order to Wino Z. This doesn't happen. It actually always goes to Wino Higgs. Which means that this decay chain will be completed with something that makes it even nicer. Bino goes to Higgs. We know this is the missing energy at the bottom of the spectrum. And so on one side, we get TT bar Higgs times 2, these are completely insane events. You know, they have 8 B's, 4 W's. The standard model background is 0. So it's not a question, and if this kind of picture is right, it's not a question of accumulating lots and lots of statistics and trying to dig something out over background. We just have to make 4 or 5 events like that, and they're sufficiently spectacular that we can know that that's what's going on. So that's the qualitative collider thing to look for, is just displacement and very exclusive kinds of decay patterns as well. That you see the Higgs but never the Z, that are indications of this simple collection of particles decaying through higher dimension operators. And of course, the other general feature about having particles up here is this is the scale that's indicated by flavor, right? I told you it's safe if things are up in the hundreds or thousands of TeV range, but again, in detail, some things could show up, other things could, so it's not so far away that flavor could be totally irrelevant. So flavor could actually be interesting in this sort of picture. And you know, if we're lucky enough to see any of these things and we get an indication of this higher scale, as I also said, we can in principle on planet Earth build colliders to go up to 10, 100 TeV and perhaps complete and see the rest of the supersymmetric spectrum. Okay, so that's all I think I'll have time for to talk about. But let me just let me just end with a qualitative comment about what the future might look like and what you as students should be preparing for. Okay. So I really think there are sort of 2 possible roads. I'm not saying anything unobvious, but there are 2 possible roads for what might happen when we turn back on again. You know, it's the end of 2015, 2016. Either it'll be the 11th hour, but naturalness will be all right. We'll see lots of particles. Everything is great. Of course, this is by far the most exciting scenario for everybody. There's lots to do, et cetera, et cetera. But for you especially, it's even more exciting than for maybe the rest of us, because you see, 10 years ago, 15 years ago, if you were sitting in your place, most people sitting up here had great confidence with what was going to happen at the LHC. It was going to be supersymmetric, this variety and that variety. And so if you're coming into the field, you sort of got the feeling that it's your job to clean up the details of what these people sort of all settled and did in their grand way, you know, 20 years ago. That's not the situation right now, right? And so, in fact, if there is something like that going on, if it is super duper natural, that means it's something a little bit weird, right? It's not something that everyone knew ahead of time what it was and everyone expected. Now, is it necessarily going to be massively revolutionary? I doubt it. It may be that there's a few singlets here or there, there's a pattern, there's another gauge group, there's something like that. But still, if we want to figure out what it actually is, no one has written it down yet. No one sort of knows ahead of time exactly what it's going to be. And so in that picture of the world, where there's a bunch of new particles or something there, not only do we have to figure out what it is, but there's opportunity to simultaneously think about the collider physics, the signals, and also at the same time think about what the underlying model could be, right? And it's the marriage of those 2 activities, what I mentioned in the first lecture. Previous times when we've had big developments in particle physics, it's been people who can do both things, know something about the theoretical structure, something about the data, not too glued to the data, not too far away in the formalism of the underlying theory, but somewhere in between, who made the really big breakthroughs. Okay? And interestingly for you, if we're lucky enough to see a lot of new particles, that's the situation that we should be in again. Okay? So in thinking about what you should learn now, extremely important to learn about the collider physics and about all of this stuff, extremely important, but actually think about what the theories might be. Have some familiar with them. What would you have to do to add 2 singlets to change this and that, and what might it buy you, and what other things it would affect, and so on. You should have some facility with that way of thinking, on the one hand. And that also goes through a little bit less so if it's something like split, because there's many fewer particles, but there'll still be a lot to think about with the structure of the higher dimension operators and what it might be telling us about the ultraviolet, how we might correlate it with other indirect observables like electric dipole moments or flavor violation. In that kind of picture of the world, actually thinking about theories of flavor and what might be going on with flavor physics at the 100 or 1,000 TeV scale becomes much more interesting and would actually be something you could do with experimental consequences on the scale of your career, if not mine. Okay? Okay, there's the other picture of the world where we turn on the LHC. We don't see anything clobbering us over the head as new physics by the end of 2015, 2016. And at that point, there's another bifurcation. At that point, you could say, screw this entire field of particle physics. I'm going to think about quantum gravity for the rest of my life, or condensed matter, or anything else you want. That's a reasonable attitude. Okay? If you continue to care about particle physics, then what will be extremely important is to think, at least I think, is to think and understand as deeply as possible QCD at the LHC, okay? And try to dig as much as you possibly can and think about any extra clever ideas that might be possible to dig under these humongous backgrounds to perhaps find things that aren't hitting us over the head. Because we all know very well, and especially the model builders among us know, we can hide massive amounts of new physics if you just give us a few operators here and there that make everything decay to Ford jets all over the place, right? So I'm not at all, I don't have a concrete strategy to tell you how to go proceed and find great new ideas for dealing with thinking about QCD and jets at the LHC, but it seemed to me that that's one of the most important things to focus on in this second picture of the world, because it could be that won't be just it won't be a nicety, it'll be absolutely, totally critical in every way to the future of the subject. So these are sort of two very different kinds of even intellectual roads to be thinking about. But I think that's also what makes it a very, very exciting time, because you have a finite, non-zero amount of time to start getting into one or both of them. And if I were in your place, I would try to get into both of them, right? You have nothing to do other than think and work hard, and so I hope you do that. Thanks.